WM plus V of X squared, anything that's even. And so this meant that any eigenvectors or eigenstates of this Hamiltonian were degenerate, that there was a double degeneracy. Anything that had a wave function with momentum p or position x had to have exactly the same energy if you reverse them. Same energy, i.e. degenerate eigenvalues. Under p goes to negative p and x goes to negative x. This is the parity transformation that turns any vector into its negative. So we can immediately see that in 2 dimensions and higher, now that degeneracy is much, much larger. Now there's a continuous class of degenerate states that doesn't care whether your momentum is along x or along y, it only cares the magnitude. And as long as your potential also doesn't care about the direction, if it only cares about the magnitude, then even for a particle and a potential, your Hamiltonian possesses 2-dimensional rotation symmetry, which is a much, much bigger class of degeneracies. So I guess maybe the point here was for the free particle at least. We had plus or minus square root 2mE. And the energy was the same either way. So in 2D and higher, any rotation P goes to P prime, where this transformation is a rotation R of theta, preserves the magnitude of P and leaves the energy invariant. This statement just about the momentum is sufficient if I'm talking about the free particle. If I'm talking about a particle and a potential, then the same thing is true as long as it depends only on the magnitude of R. So since we know that there's a symmetry transformation under which these eigenvalues are degenerate, we'd like to find a commuting operator so that we can simultaneously diagonalize those states and find a complete set of commuting operators to characterize the state with certain radial properties and the state with certain angular properties. So specifically, the transformation that we're going to use here, right? So this is one that takes some vector r with, let's call it angle alpha. I want to rotate the entire thing by an extra angle theta. So this is my r prime, or I could call it p and p prime, either way. So note here that the new components are x prime equals r, the radius didn't change, cosine theta plus alpha, and so this is r cosine theta cosine alpha minus r sine theta sine alpha. And in terms of the original components, r cosine theta is x, and r sine alpha is y. And similarly, I get y prime equals x sine theta plus y cosine theta. I wanted to spell this out very explicitly because it's very easy to get tripped up on which sign goes where, and those things just differ by a convention of active versus passive transformation. So this picture is an active picture. Separates very easily. Okay, so the symmetry group of such transformations is one that we've already studied in detail. So this is the 2D rotation group. Called SO2, the special orthogonal group of 2x2 matrices. The elements of this group are the 2x2 matrices R of theta, which one can write as cosine theta, negative sine theta, cosine theta, which corresponds to that active transformation. And under this transformation, your position vector R, which has components x, y, gets transformed into R prime by multiplying it by that 2x2 matrix specified here. And the same happens to the momentum. So we would like to use the symmetry properties of this transformation to constrain or label the degeneracy of the rotationally symmetric Hamiltonian. So here's the rub. What does it do to the eigenvalue equation? So the critical point is that this mapping with this matrix on these vectors, this is the transformation of the eigenvalues. This is the ordinary numbers that are constructing ordinary vectors. This is not the same thing as what's happening to the quantum states. And this is a very subtle distinction that took me many years to understand after I went through this the first time. So this is part of what I've been aiming at in trying to explain the role of symmetry throughout this class. So the eigenvalue equations were R operator on R eigenstate equals R eigenvalue, same eigenstate back. And similarly, P operator on P eigenstate equals eigenvalue, P eigenstate. How did these things transform under this rotation operation? Well, the operator is still the operator. This is just the operator that tells me what the position of something is. This transformation is telling me that the new position, the classical style number, gets rotated just like on the left-hand side of the board. So this equals R prime times an eigenvector. Similarly, P, the operator hitting the eigenstate, transforms to give me the rotated eigenvalue times the quantum state. But none of this tells me what the heck goes inside here. And the answer is not necessarily obvious. These quantum states transform in a different way that is connected to this transformation, but not identical to it. Thankfully, we've already constructed how to go from a classical transformation and the symmetries thereof to the quantum version of the same transformation. Is this point clear? I want to emphasize that there are two different transformations. This is the orthogonal rotation of the two vectors. This is a unitary transformation of the quantum states, and they are different things. All right, so we spent quite a lot of time constructing the following statement. For any observable omega, the effect of the symmetry transformation generator G, where G, the generator, is the quantity that is conserved under that symmetry. So omega of A, some parameter of the transformation, is obtained by exponentiating the Poisson bracket with the generator times that parameter A times omega naught. So I should mention now that the next steps here will very strongly parallel the steps that we went through in lecture number 19 when we constructed the Schrödinger equation out of the Heisenberg picture from canonical quantization. We are now going to do basically the exact same thing for a different symmetry transformation. Cross-reference lecture 19, where we obtained Schrödinger equation, the time evolution operator, the Heisenberg picture, all of that jazz from canonical quantization. Because that prescription tells us how to take this extremely general statement about symmetries and observables and bring it into quantum land, where it will tell us what's happening to the quantum states. So under canonical quantization, that statement about generators and observables reads omega hat after transformation A is written as e to the minus I over h bar bracket commutator with the generator G now as an operator and parameter A acting on omega naught, the untransformed observable. So this is standard canonical quantization that takes a Poisson bracket and replaces it with 1 over I h bar commutator and promotes everything to operators. And we saw that in classical mechanics, where everything is written in terms of Poisson brackets, that very weird-looking formal solution is the best we can do. But once it becomes a commutator, I can rearrange these terms and write it much more compactly as e to the plus I over h bar generator parameter acting on the state, e to the minus I over h bar generator parameter. This is exactly what we did when we obtained time evolution, where the time evolution of something was controlled by the Hamiltonian, and this quantity became the time evolution operator u of t. unitary transformation that carries out time evolution and evolves the state forward in time. And you can see basically nothing about this statement is going to change now that we're considering a different symmetry transformation. So for rotations in the xy plane, we already know what the conserved quantity is. What is it?
Momentum.
Not linear momentum.
Angular momentum.
Angular momentum. Which component of angular momentum?
Z.
Go ahead.
Z component.
The Z component, yes. The conserved quantity is LZ.
Does that turn this into a three-dimensional problem then? Or just like only technically?
No, so this is still rotations in 2 dimensions. You can think of all of this as sort of, scalar rotations. This is just some operator. You don't necessarily have to call it LZ. The LZ assignment is only meaningful when we think about how to extend this into 3 dimensions. But you can see where I'm going with this, that this statement and the process is also going to work the same way when we go to full 3-dimensional rotations, or 4-dimensional Lorentz transformations on space-time. So yes, for now we're doing 2 dimensions. The key nice feature about rotations in 2 dimensions is that the group is abelian. The group commutes because you're always rotating about the same axis. So if I rotate by theta 1 and then by theta 2, the order doesn't matter. But it does matter when I go to 3 dimensions and I may have rotations about LZ and then about LX. That will be the new layer of complication when we go to 3. Okay, so the transformation classically then is that any observable after rotation by an angle theta is obtained by e to the Poisson bracket with the angular momentum LZ. The parameter is the angle theta, which is the canonical conjugate of that momentum, times omega naught. And so we can immediately write down the quantum version of the same transformation, now acting on quantum states. Omega hat of theta is e to the plus I over h bar angular momentum operator times theta, untransformed observable, e to the minus I over h bar, LZ theta. Exactly the same way we did in lecture 19 when we wrote this down for the time evolution operator. Recall also that when we switched from that active picture of the transformation where the operator was the thing changing to the passive version of the transformation in Schrödinger picture, this unitary operator was the one that became the time evolution operator. This is the one that's going to transform the states. So this is the unitary operator U of theta that will act on a quantum state and rotate it around to perform the same quantum version of the rotation that is classically generating those 2x2 rotations. So the statement about how to make this identification is the same as we did when we went from Heisenberg picture to Schrödinger picture. We said it doesn't matter how much I consider the observable to rotate versus how much I consider the quantum states to rotate, as long as the matrix elements always rotate the same way. So if I have omega ij of theta is my observable in the basis state I of the transformed observable omega of theta j, when I plug in this transformation, this is I plus I over h bar LZ theta, omega naught, the untransformed state, or untransformed observable, e to the minus I over h bar LZ theta acting on basis state J. And it doesn't matter whether I consider this combination of operators as rotating the operator omega with the same fixed basis, or I consider the basis states to have rotated and the operator not. So again, this is the difference between an active versus passive transformation, but this statement is the answer to that very subtle and confusing question about how is the rotation of the classical object, like that 2D vector, related to the same rotation of a quantum object. And I want to be very clear that the reason that this works is because the algebra of the rotation is the same. That when I write down the classical transformation, the algebra of that Poisson bracket with the generator is what achieves the whole transformation. And nothing tells me that quantum mechanics has to be given by commutators. But if symmetries work the same way, if they have any ability to correspond to each other classically in quantum, they have to be different representations of the same algebra. And so by formulating this as the algebra of classical mechanics, the algebra of quantum mechanics is the same, even though everything else about it is different. So this is the answer to the question about how the quantum states transform. So let's revisit that eigenvalue formula. So two different formulations of the same transformation. You can formulate rotation of the operator. Any omega under this rotation, r of theta becomes e to the I over h bar Lz theta omega naught e to the minus I over h bar Lz theta. Or equivalently, the quantum state psi upon that same rotation becomes e to the minus I over h bar Lz theta. So it's either this picture or that picture. They are equivalent, but don't do both because then you're double transforming or you're transforming on transforming. This is again the difference between an active versus passive picture of the transformation. So applying this tells me that my quantum state R, that was an eigenvector of the position operator before the transformation, after rotation becomes e to the minus I over h bar Lz theta acting on that same quantum state. The same is true for the momentum basis. All of the information about how position and momentum are different from each other is completely contained in how the Lz operator differently acts on position versus momentum. And so notice that Lz is built out of combinations of position and momentum. So it will do different things to the position basis and the momentum basis. Okay, so does this work and does it make sense? Does it do what it's supposed to do? Sanity check. Does it work? So the easiest place to check is for an infinitesimal transformation. Theta gets replaced by epsilon, and epsilon is small. Under this transformation, that 2x2 rotation matrix R of theta, I guess it becomes now R of epsilon. This is cosine epsilon, negative sine epsilon, sine epsilon, cosine epsilon, and for small epsilon, this is just 1, negative epsilon, epsilon 1, up to corrections of order epsilon squared. The quantum operator, the unitary operator, u of beta, that performs the rotation on the quantum states is now u of epsilon. This is e to the minus I over h bar Lz epsilon. And if epsilon is small, then I can expand the exponential. This is 1 minus I over h bar Lz epsilon plus order epsilon squared. And I guess it's worth plugging in specifically what Lz is, since we're going to immediately apply that. This is x y minus y dx operators. So what does this do to the quantum state? Does it transform as expected? So that we want to see, maybe this is a good place to put it. If I take the position operator and apply it to the rotated state, u of beta r, this should equal the rotated vector r prime times the same quantum state value. And similarly, for the momentum vector, I should have p operator acting on the rotated state u of beta. I want to test and see, is this equal to the rotated momentum p prime with that new rotated state as the eigenvector. All right, so let's try it out. Let's apply u of epsilon to the position state r. So we said this operator for small epsilon is 1 minus I over h bar x y epsilon plus I over h bar y x epsilon acting on the state r, up to epsilon squared corrections. Okay, now maybe it helps if I write that state r as x comma y. It's simple to know what x and y operators do to that quantum state. However, I have py and px sitting next to them. What am I going to do? I need to somehow put x and y next to that quantum state so I can act on it and use the fact that it's an eigenvector.
They commute.
They do commute because it's the wrong combination. It's x and py. And from canonical commutation relations, these guys commute just fine. These guys also commute just fine. It's only x and px that do not. So we're in business, I can just allow x to act on that quantum state and return the eigenvalue x with no how. 1 minus I over h bar. Let me write this as py x epsilon plus I over h bar x y epsilon. Okay, there's a few different ways that you could see this, but the way that I like the most is to recognize that the transformation generated by momentum is the translation operator. So we know what this combination is going to do. The translation operator, we wrote of A was, let's say, AX for a translation along the x-axis was e to the minus I over h bar px operator A. So an infinitesimal transformation tx of some small epsilon is 1 minus I over h bar px epsilon plus order epsilon squared corrections. What I want to do is I want to identify this term as a translation of the state along y by an amount x epsilon. And similarly, I want to identify this as a translation along x by an amount whose magnitude is y epsilon. So to make that explicit, within this accuracy of order epsilon squared, I'm going to rewrite these things as a product of exponentials. Of epsilon, the rotation on quantum state R is 1 minus I over h bar py x epsilon plus corrections of order epsilon squared times another 1 plus I over h bar px y epsilon plus corrections of order epsilon squared, acting on the state xy. If I open up these parentheses and distribute it back out, I get 1, and 1 gives me the 1 and the I h bar px gives me this, the 1 and the minus I h bar py gives me that, and the cross terms are higher order and are neglected. So what we found is that the unitary operator that performs a small rotation by an angle epsilon can be written as the translation operator. This is e to the minus I over h bar py with an amount x epsilon. The second factor is e to the minus I over h bar px with an amount negative y epsilon, acting on the quantum state xy. Again, with corrections of order epsilon squared. So I simply identify this as a translation along the y-axis by an amount plus x epsilon, a translation along the x-axis of an amount negative y epsilon. And I know what that does to the quantum state. This just gives me a new quantum state that displaces x by minus y epsilon, and it displaces y by plus x epsilon. And this is basically the answer. You see that it works. We'll hit it with the position operator momentarily to finish the proof. But the rotation has taken x minus y epsilon, that's the 1 and the minus epsilon from the rotation matrix, and that's the epsilon plus 1 from the second row of the rotation matrix, R of theta. So then if I take R operator and I hit it on U of epsilon R, we just found out what that quantum state is. This is R operator on this state, x minus y epsilon y plus epsilon x. The position operator just returns this eigenvalue. So this is x minus y epsilon in the I direction, plus, let me write this as epsilon x plus 1 y in the j direction, times the quantum state back, which was u of epsilon r. So this is the transformed vector. R prime is equal to, let me write it, x prime, y prime equals 1 minus epsilon, epsilon 1, x, y. And this is that rotated R prime that we wanted to see. So this shows that, yes, the algebra has carried over correctly from rotation of vectors in two-dimensional ordinary space to highly abstract rotation of quantum states generated by commutators. Any questions about how this has worked? Okay, so as we've seen, all of this has been generated by the commutator algebra. Directly following commutation. So the basic ingredients are the operator definition of LZ, as well as the canonical commutation relations among x, y, and px and py. Boy, this burns through some film. So this gives us a commutator of x with the generator LZ. Commutator of x with x, y minus y, x. Out of all of these four objects, there's only one thing that x does not commute with, and that is px. This part of the commutator is 0, and y is a constant as far as this is concerned. So this is negative y, commutator of x with px. And so this is minus I h bar y. Similarly, commutator of y with LZ. The only piece y does not commute with is py, and so this gives me a plus I h bar x. And this is sort of the picture of that rotation where you saw that there was a minus epsilon from the y contribution and a plus epsilon from the x contribution. That's sort of what's being indicated here. That the effect of the generator on x is to subtract a little bit from y. The effect of the generator on y is to add a little bit from x. Similarly for the momentum, we didn't work out the case of how this unitary operator acts on the momentum state, but if I just write down the commutation relations, you'll see that it's exactly the same. Commutator of px with LZ. The only thing that it doesn't commute with is x. So I get px, x, and py popped out the back. This is the commutator that gives me IH bar, but it's in the wrong order, so I get a minus sign. And likewise, PY with LZ. The only thing PY doesn't commute with is Y, and so I get minus commutator of, bring up the Y in front, commutator of PY. Sorry, I'm writing the wrong thing. Okay, try it again. Y doesn't commute with, PY does not commute with Y, so PX is what pops out the back. So I get minus commutator of PY with Y, with PX behind it, and this is again minus IH bar. So I get plus IH bar PX. So we see the effect of the generator to rotate X and Y. I get minus IH bar Y, same as the momentum. X with the generator minus IH bar PY. So exactly the same way that it rotates position, it will also rotate momentum. Okay. How am I doing on time? Great. All right, so the bottom line from all of this is that any Hamiltonian which is rotationally symmetric must commute with the rotation operator, and therefore it commutes with angular momentum. What I mean is, if I have the Hamiltonian on some state psi that is an eigenstate with energy E, then if I have the Hamiltonian on a closely related state, which differs only by a rotation, this also equals energy times the same state back. Copy that over here so I'm not squeezing it into the corner. So that was H U of theta psi of theta psi. But E is the energy eigenvalue obtained just from H. So E is just a number. I can pull it past U. This is U of theta E psi. And E psi is just the action of the Hamiltonian on psi. So this is U of theta H psi. Psi equals UH psi. So if I subtract them over, this is telling me that the commutator of a Hamiltonian with the rotation operator is 0. And we know what the rotation operator is. This is just exponential of angular momentum. And if this is true, not for some magical value of theta like 90 degrees only, but for any theta, this can only imply that the Hamiltonian must commute with angular momentum itself. Rotational symmetry implies that the Hamiltonian commutes with the generator of the symmetry transformation. And so this means that the Hamiltonian and the z component of angular momentum are simultaneously diagonalized. And so that then I can label my quantum states as quantum states that have a well-defined energy and that have a well-defined z component of angular momentum. Okay. So the eigenvalue condition for angular momentum leads to quantization of angular momentum, which we'll see next. Momentum. So to see the action of the angular momentum operator in differential form, it's easiest to write it in polar coordinates. So let me take the rotation operator. Rotation operator on some state psi, and I'm going to write this in polar coordinates with variables r and phi. So that is just the 2D position vector state written in polar coordinates. We know what the rotation operator does. It rotates the angle by theta. So I'm going to write this as r phi dagger of negative theta psi. I don't think I have it anywhere on the board now. So let me write it again. U of theta was e to the minus I over h bar LZ theta. U dagger of theta is e to the plus I over h bar LZ theta, and that's the same as if I just took theta to minus theta. So what I'm using here is U of theta equals U dagger of negative theta. It's like saying if this thing is rotating the cat, then it rotates it by positive theta. It can also be considered to be acting to the left on the bra, where it rotates the bra by negative theta. That's what I'm doing here. So this is the dagger of this thing acting on the position basis. And so this gives me r phi minus theta. Psi. All right, so that's what the rotation operator does here. If I have so I want to write this shift, right? So this is the function psi of r phi minus theta, and I can write that shift by an angle theta as a derivative. So this is r phi to the minus I over h bar LZ theta. Psi is equal to e to the, I shift by an angle negative theta. So this is e to negative theta, dd theta acting on the function psi of r and phi, all this phi here, shifting the angle by negative theta. And I want to identify this with the action of LZ. So this is the same as say e to the minus I over h bar minus I h bar dd phi theta acting on r phi. So the position representation of the angular momentum operator looks just like the position representation of the linear momentum. Theta now is minus I h bar dd theta psi of r. This is completely analogous to the case of linear momentum, where we said Px acting on the state psi can be written as a derivative minus I h bar ddx acting on psi. So this is again sort of like saying LZ is a momentum, it's a generalized momentum, and so it generates translations of its conjugate variable, which is the angle theta. And so just applying this to the eigenvalue condition immediately is going to give us quantized angular momentum. So if I have LZ operator acting on its eigenvector, returns a definite eigenvalue times the same eigenvector back. If I write this in polar coordinates, then this expression is minus I h bar dd theta on the wave function equals the same function back times that eigenvalue. And this is easily solved as a plane wave, the same way that we did in one dimension for the eigenstates of momentum. These are plane waves in the angular variable theta. So LZ R theta just solves this trivial first order differential equation. And let me say this is proportional to e to the I over h bar eigenvalue LZ theta. And this immediately gives us quantization of angular momentum from the requirement of continuity. Right, so this is e to the 2 pi I LZ over h bar must give me 1. And so this tells me LZ must be quantized in integer units of the angular momentum. Okay. So the quantum number m is referred to as the magnetic quantum number. Since the angular momentum of a charged particle aligns with its magnetic moment, and the magnetic moment couples to an external magnetic field. So the properly normalized eigenstates are Lz in terms of the quantum number m is mh bar times m. That properly normalized state in polar coordinates has a factor of 1 over square root of 2 pi, because you integrate it over the angle of 2 pi. And that normalization ensures that two different states with different quantum numbers m and m prime are orthonormal. So to wrap everything up, let me say that the Schrodinger equation for a rotationally invariant Hamiltonian gave us Hamiltonian on a state with energy E and quantum number m m Lz on em is mh bar em. And plugging in the eigenfunctions of the angular momentum operator, this tells us that the state em in position space must be some function of the radial coordinate f of r, and the angular behavior must be e to the I m theta. You can include or exclude the factor of 1 over square root of 2. And I don't want to work through the details, but suffice to say that if I now plug in this Hamiltonian form, if I have h equals e squared over 2m plus e of r, then in position space, this becomes minus h bar squared over 2m, Laplacian of psi plus e of r psi equals e psi. And if you plug in this form for the eigenfunctions with angular momentum Lz, then you eliminate the angular component of the Laplacian. So in spherical coordinates, this gives you simply, let's say, minus h bar squared over 2, all right, capital M for the mass here to distinguish it from the magnetic quantum number m. 1 over r, f, r, minus r squared plus r f equals f. So essentially, knowing the angular behavior allows you to plug it back in and get just a radial equation for the Schrodinger equation. Where now the well-defined properties of angular momentum appear as a contribution to the energy. This is called the centrifugal barrier in classical mechanics. It's just the rotational kinetic energy associated with having that value of the angular momentum. And once you boil down the Schrodinger equation to a one-dimensional radial equation, now you can revisit all your favorite old problems, plane waves, particle in a box, two-dimensional harmonic oscillator, and solve similarly the one-dimensional radial equation, just like we did for one dimension. Okay, thank you for your patience. I'll stop here. Any questions or comments? All right, thank you very much. Everybody be safe, have a nice Thanksgiving break, and I will see you one more time for the last week of real classes.